This is the last lecture of COS 212, where we'll be dealing with Chapter 13 on string matching. We will only be covering the beginning of Chapter 13, leaving out the more advanced string matching algorithms. Now, we've dealt with the problem of searching for a particular key value within a data structure several times during this course. And what we've seen is that this is a relatively difficult task. So, for example, if we're dealing with an unsorted data structure, then we need to perform a sequential search, which is very inefficient with a complexity of O(n). If we have a sorted data structure, something like a sorted array or a sorted linked list, then we can use the binary search algorithm, which improves our efficiency to O log base 2n. And then if we use the even more advanced data structures of hash tables, we can then reduce searching to a direct access operation in an array, which has a complexity of O(1). However, if we're dealing with text data, then the question arises, what if we are looking for a word in a large body of text? So in other words, can text then be considered to be a kind of data structure? Now, the kind of data that we'll specifically be considering in this chapter is language. And of course, language, as we know, is the main communication medium for humans. Now, in the context of this chapter, we will generally be referring to English as the language that we'll be working with, but obviously these concepts also extend to any other language. So what we see when we consider a language is that generally languages are fairly complex, and they're usually too complex to be represented by means of the kinds of data structures that we've discussed so far through this course. And the reason for this is that language's structure is just generally complex in nature. We have, for example, different forms of words. So, for example, we might have the word match, and we have different forms which are indicated in English by different endings to those words. So, for example, we have match, matches, matching, and so forth. Additionally, we also have the concept of compound words, which are words that are constructed out of other words. For example, footpath is constructed out of two words, foot and path. And we may want to, for example, search for the subwords. For example, we might want to search for foot within footpath and other text as well, or we might want to search for the entire term. So this obviously then increases the complexity in terms of how we would need to represent language, and also how we would have to go about searching these language representations. So this leads us then to the concept of string matching, which is what this chapter deals with. And string matching then is the process of looking for a particular subset of text in a large text file. So for example, if you have an entire book or a series of books, then we may be interested in finding a particular occurrence of a word, or possibly several occurrences of that particular word through this body of text. So the question then is, what is the fastest way for us to automate this string matching process? At this point, I'd like to take a moment to discuss some general issues related to the algorithms discussed within this chapter. So it's very important to note that the algorithm pseudocode provided in these slides differs in a number of respects from the pseudocode that is provided in the textbook. And this is due to a number of errors within the textbook's pseudocode algorithms. So it's very important that you refer to the algorithms as presented within these slides and not within the textbook. And in particular, for the exam, when answering questions related to this material, you should refer to the algorithms provided in the slides rather than the textbook. So this is important for all of the algorithms. However, it's particularly important for the last algorithm that we'll be discussing, which is the Knuth-Morris-Pratt algorithm. The Knuth-Morris-Pratt algorithm also uses a method defined right at the end of this lecture called find next, and there are also errors in the find next method. So these errors then also extend to the textbook's discussion on the time complexity of the Knuth-Morris-Pratt algorithm, and therefore that discussion is also inaccurate. So once again, please refer to these slides as far as the time complexity analysis of the Knuth-Morris-Pratt algorithm goes. In general, a string matching algorithm searches a body of text, which we will refer to as T, for a specific pattern, which we'll call P. Now, for our discussion, we are specifically interested in exact string matching algorithms. So what this means is we are searching for the full pattern P within our text T. In other words, we are not searching for something that is close to the pattern P. Now, it turns out that there is a whole family of string matching algorithms which deal with these kinds of approximate matches, but these are beyond the scope for our current discussion. Now, obviously, there are a large number of different string matching approaches that could be used, and we are only going to be considering 3 of these, the first of which is the simplest, most naive approach. So this approach is usually referred to as the brute force string matching algorithm. And the brute force algorithm works by running through our text T letter by letter. And then for every letter within our text T, we compare our pattern P to T one letter at a time. Now, if a mismatch is found, what this means is we found a partial match, but the match is not complete. So what this means then is we need to continue searching for another match that is complete, and we do this then by resetting our pattern P, so that we begin matching from the beginning of the pattern again, and we continue searching our text T from the point just following the beginning of the partial match that we found previously. All right, so this is what the brute force string matching algorithm looks like in terms of pseudocode. You can see that we have 2 counter variables I and j, and these represent then subscripts, where I represents the subscript within the text T that we're searching, and j represents the subscript within the pattern P that we are searching for. So we begin then by setting I to 0, meaning that we begin our search at the beginning of the text T that we are searching. We then enter this outer while loop over here. So this while loop continues executing while I is less than or equal to the number of characters within the text T minus the number of characters within the pattern P. So all that this loop's condition ensures is that we continue searching while there are still sufficient characters remaining within our text T for our pattern P to fit into. So for example, if the pattern that we're searching for consists of 5 characters, then we will stop searching as soon as we have fewer than 5 characters remaining within T. And the reason for this is because the pattern of 5 characters cannot then possibly exist within the remaining characters within T. So then for each iteration of this while loop, we are now searching for a match. So we set j's value to 0, which means that we are searching from the beginning of the pattern. We then enter this nested while loop over here. So this while loop then continues while j is still less than the number of characters within the pattern P. What this ensures is that we don't continue then attempting to find matches within our pattern beyond the end of our pattern. Then additionally, we have this part of our condition here, and this compares our text T at subscript I to our pattern P at subscript J. So in other words, this loop will then continue executing while there are still matches between our text T and characters within our pattern P. So as long as a match then continues occurring, we then increment i's value by 1 and also j's value by 1. What this means then is we are now comparing the next character within our pattern to the next character within our body of text. Now, once this while loop terminates, then one of two things has taken place. Either we have found a complete match for our pattern, in which case our algorithm has been successful, or we have not found a complete match. We found a partial match so far, but the match has failed because there's a mismatch between at least one pair of characters within T and P. So this if statement following the while loop then tests to see what the reason is for the while loop terminating. So it tests to see whether j is equivalent to the number of characters within P. And if that is the case, then what this means is we have then reached the end of our pattern, meaning that we've matched every character within our pattern to characters within our text T. So in this case, we then return a match, and we also need to indicate where the match begins. So we compute that by taking i's current value and subtracting from that the number of characters within our pattern P. So all that this does then is it takes i's current value, it subtracts the number of characters within our pattern from that, and that gives us then the subscript within T where the complete match started from. Now, if we reach this point within our algorithm's execution, this means then that we have found a partial match or possibly no match at all. But the point is we haven't found a complete match yet at that point. So at this stage, we then need to update i's value, and we update that to i's current value minus j plus 1. And what this then computes for us is the subscript within the text T just following the start of the partial match that we have currently found. Now, this matching process then continues, and once this loop, then the outer loop terminates, this then means that we don't have then sufficient characters remaining within our text T. So at this point, we then have no matches that have been found at all, and there are no further matches that can occur within our text T. So we then need to return a report indicating that a match has not been found. So let's look at the operation of this brute force string matching algorithm in terms of a simple example. Over here, we have our text T that we are searching, and we have also our text P, which is the pattern that we're searching for within T. So we start off then initially with I and j both having a value of 0, meaning that we're starting to search our text at the very first character, and we're also beginning to attempt to find our match within P with the first character of that pattern. So now we enter our nested while loop, and we are now comparing the character at subscript I within our text T to the character at subscript j within our pattern P. We see that those characters which are highlighted red over there match, so this means we then need to advance both I and j by 1. So we're now comparing the character B to B within the text T and the pattern P. Again, we see that we have a match, so we again need to then advance I and j by 1. And at this point, we see then that the text T at subscript I is A, whereas the character at subscript j within our pattern P is C. So at this point, we then have a mismatch. So what this means then is we have only a partial match for our pattern, which means we then need to reset our subscript j to the beginning of our pattern, whereas the subscript I needs to move to the character just following the start of our partial match. So our partial match then is the text ABA, and we then need I to refer to the character just following the start of this partial match, in other words, the character B. So that's exactly what we've done there. We now need to again continue and attempt to find then a match between P and T. So we compare then the characters at subscripts I and j. We see that those don't match. So j then remains the same, whereas I then is advanced to refer to the next character. We then again compare the characters in T and P, and we see that they match again at this point, which means we've now found a partial match. So we now need to advance I and j by 1 and again compare the characters. Again there we find that they match, so we advance I and j by 1 again. And then for the third character in our pattern P, we see again we have a match against our text T, so again we advance I and j. At this point, we've reached the last character within our pattern P, but we see now that we have a mismatch because we're comparing the characters C and A. So again, at this point, we then need to reset J so that it refers to the beginning of our pattern P, and our subscript I needs to be reset so that it refers to the character just following the start of the partial match that we found. In other words, this character B over here within our text T. So that's exactly what we have done there. Again, then we continue with our matching process. So here we have a mismatch, so we just advance I. Again, here we have another mismatch, so we just advance I. And here again another mismatch, so we advance I again. Now at this point we see again we have then a match between the two characters in T and P. So what this means is we need to then advance both I and j by 1. Again, then we compare the characters that are referred to. We see there's another match, so we advance I and j. And then a third match occurs, so we advance I and j again. And then for the final character, we see again that we have a match, so we advance I and j once more. So at this point, j is now referring to one position past the end of our subscript P, and our inner loop then terminates. So now we test our condition over here, and we see that j is in fact then equal to the number of characters within P, indicating that we've exhausted all of the characters within P, which means we have now found a complete match. So we then need to compute the subscript of the start of our match. So we take i's current value and we subtract from that the number of characters within P, which then gives us the subscript of A over here, which is the beginning of our complete match, which I've highlighted in blue over there. So at this point then our algorithm terminates, and it terminates with a complete match of our pattern P. So the next question then is, what is the time complexity of this algorithm? Well, there are basically two main components. There's the outer loop over here, and then this nested while loop within the outer while loop. So the outer while loop, as we've seen, is responsible for advancing I through all of the subscripts within our text T, obviously excluding subscripts that our pattern P could not start from because there are too few remaining characters within T. So essentially the number of times that this loop then will execute is the number of characters within T minus the number of characters within P. But because we're interested in asymptotic complexity, we can say that the outer loop executes approximately the number of times equivalent to the number of characters within our text T in that case. Our inner loop over here is responsible for running through our pattern P. So obviously the completeness of that match, in other words, the exact number of times that for each iteration of the outer loop, the inner loop will execute, depends on the nature of the text and the pattern that we are searching for. However, we can say in general, because once again we're interested in asymptotic complexity, this inner loop will execute approximately each time the number of times equivalent to the number of characters within our pattern P. So this then gives us an overall complexity of the number of characters within T multiplied by the number of characters within P. So this is then the overall complexity. Not a very efficient algorithm, but it does work and it does successfully find matches for the pattern P within the text T. So the next obvious question then is, can we possibly somehow modify the brute force string matching algorithm so that it can perform the same task but do it much more efficiently? A fairly simple improvement to the performance of the basic brute force string matching algorithm was proposed by Hancock. Now, Hancock's algorithm uses the same basic strategy as the brute force algorithm does, in that it compares pairs of characters where one character is selected from the text T and the other character is selected from the pattern P. Where Hancock's algorithm differs, however, is in terms of the order that these comparisons take place in. So the comparisons begin from the second character of our pattern P and the second character of our text T, and move forward until the end of our pattern P is reached. If all of these characters match, then the last comparison is between the first character within P and the first character in T. Now, this may seem like a fairly pointless modification, but it in fact allows us to introduce an optimization on how I is updated after a mismatch is found. And this optimization then is based on whether the first two characters in our pattern P match. So there are four cases that we need to deal with. The first two cases are for when the first two characters in our pattern P are not equivalent to each other. So in this example, we can see that our pattern P has two characters starting at A and B, and those two characters are not equal to one another. So the first case then that we need to deal with is where our text T at subscript I plus 1 is not equal to our pattern P at subscript 1. So these characters then are highlighted in red over here, and we can see then that they are the character just following subscript I in T and the second character in P, and we can see that these two characters don't match one another. So at this point, we then have a mismatch and we have no further information. So we then proceed in exactly the same way that the brute force algorithm would have, where we increment index I by 1 and then we start the search again to try to find another complete match. So in our example over here, we would then increment I so that it no longer refers to the first character in T, but the second character, which is a D over there. The whole matching process begins again then from this point on. The second situation again is where the first two characters in P do not match. As we can see in our example over here, the first two characters in P don't match one another. However, in this case, we're now looking at our text T at subscript I plus 1, and that is equivalent to the character at subscript 1 in our pattern P. So over here we can see those two characters again are highlighted in red over here, and as you can see, they match. So at this point we now have a partial match based on the second characters within T and P. So what we then need to do is look ahead within T, matching P character by character, and then assuming that we match all of the remaining characters in our pattern P, then we need to compare the first characters within T and P. And if those then also match, we then have a complete match, which means that we can then report that a match has been found and terminate our algorithm. However, if a mismatch then is found at any point during the look ahead, then we need to again fail our match and then advance I. So in this example over here, we would then have matched the second characters within T and P. The next two characters highlighted in green over there do match, but then on the third pair of characters that we compare, we see that a mismatch has now occurred. So at this point, our partial match has then failed, but now we can make an observation. So we see then that T at subscript I plus 1, as we've noted in our original condition over here, is equivalent to P at subscript 1. So in other words, these two red characters match. But we also know then that our subscript 0 within our pattern is not equivalent to the character at subscript 1 within P. In other words, these two characters don't match. So what this means then is that we already know that T at subscript I plus 1 cannot be equivalent to P at subscript 0. So in other words, these two characters over here then cannot match. So what this means then is that it's pointless to continue the comparison from the next character within our text T, in other words, this D over here. And what this then implies is that we can in fact then skip our index I ahead by 2 places rather than 1, and then start the search again. So if we look at our example then, I is at this point referring to A, the first character within T. We can now increment it by 2, skipping over D, so that we continue our comparison from the green A within our text T. We then continue our comparisons trying to find a complete match in exactly the same way as we just did. We can now consider the last 2 remaining cases that Katz's algorithm needs to deal with. Both of these cases deal with a situation where the first 2 characters in our pattern P match one another. So in this example, you can see we have our pattern P here, and the first 2 characters are both B, meaning that they match. Now, the first of these 2 cases is a situation where our text T at subscript I plus 1 is not equal to our pattern P at subscript 1. Once again, these 2 characters are highlighted in red over here, and you can see that the characters do not match. So here we can again make an observation similar to the one that we made for the second case on the previous slide. We know that the 2 characters highlighted in red do not match one another, and we also know that the first 2 characters in P match one another, which implies that the character D, in other words, the character at subscript I plus 1 within T, can also then not match the first character in our pattern P. So what this implies is that we have a failed match at this point, and it is senseless for us to attempt to find another match starting at subscript I plus 1 in our text T. The reason for this is that we are guaranteed at the very least to have a mismatch between the character at the next subscript, in other words the character D, and the first character within our pattern T. So a match from that point on, from subscript I plus 1, is senseless, which means that we can then skip over, in the example, the red character D within T, and we can increment I by 2 spaces and then start the search for a match again. So in our example over here, I currently refers to the character A at the start of T. We can then skip over D and increment I, so it refers to the second A in the text T. The final case is again a situation where the first 2 characters in our pattern P match one another. However, now we have a situation where the character at subscript I plus 1 within T matches the character at subscript 1 in P. So again, you can see those 2 characters are highlighted in red, and they match one another. So at this point we have a partial match, which means we need to then continue with the look ahead and try to find a complete match. So we look ahead then within T, and we match T character by character against the characters in our pattern P. Now, if we manage to match then all of the remaining characters to the end of P, then the final comparison that needs to take place is between the first character within T and the first character within P. So if that match then also succeeds, we have a complete match, and we can then report the match and terminate the algorithm's execution. However, if we have a mismatch that occurs at any point, then this needs to be dealt with by moving I to the right. So in this example, we can see we have a match between the two red Ds. We also have a match between the two green As. But for the third pair that we compare, we see that the B and the A do not match one another, and therefore we have a mismatch. So at this point, we need to then move I along, but we don't have any additional information. In other words, our pattern P could potentially match from subscript I plus 1 within T onwards. So what this then implies is we can't perform a skip based on I moving to the right more than one single space, and therefore we increment index I by only 1 and then start the search for a complete match again. So if we look at our example, we have I currently referring to the first character within T. We can then only increment it by 1 position, which means that it now refers to the red D within our text T. All right, so those are then the 4 cases that we need to consider. Overall, then, the difference between Handcart's approach and the brute force approach is that with Handcart's approach, we can sometimes take a step of 2 within our text T instead of just a step of 1. So this optimizes then our search process slightly because we are skipping more characters than we did in the case of the brute force algorithm. Now, what is then the overall complexity? Well, in the worst case, we have a complexity which is equivalent to our brute force algorithm. So not a very good performance once again. However, typically we will do better than the worst case, and it's been shown experimentally that on average, Handcart's approach performs better than the brute force approach. We'll now consider the third and final string matching algorithm that we'll be discussing in this lecture. This algorithm is referred to as the Knuth-Morris-Pratt algorithm. So let's consider the example that we have on the slide over here. We have our text T and our pattern P. Now, at this point, we assume that we have matched through the first part of P, and this has been matched against our text T. So in other words, we've matched through the characters A, B, C, A, and B within T, and we've matched those against the same characters in our pattern P. However, we see then that the last pair of characters does not match. So this means we have at this point found a partial match which has failed, and so we need to move on and try to find another complete match of the pattern P within T. Now, as we've seen, the brute force algorithm does this by shifting I 1 position to the right from the start of the partial match within T. So our partial match begins at the character A over here, and we then need to move I so it refers to the next character to the right of that. So in other words, I is then updated to refer to the character B, the second character within our text T. J, on the other hand, within our pattern P is updated to refer to the first character. Right, so we saw then that Handcart's algorithm attempted to optimize this process by sometimes skipping more than one character to the right within our text T. Now, the Knuth-Morris-Pratt algorithm attempts to perform the same kind of optimization. However, it tries to shift as far to the right as possible within our text T and our pattern P. So let's look at our example and see how far ahead we can skip. Now, we can see then that we've already matched past A, B, C, A, and B, both in T and in P. So we assume that those characters have already been processed. What we can then observe is that the B and C within T that we've already matched past can't match the first 2 characters within P. So in other words, we can skip over the characters B and C in our text T. We can also see then that the characters A and B within our text T match to the first two characters within our pattern P. So this means we can skip over both of those pairs within T and within P. So what this then means is that I can move ahead to refer to the character A, as you can see over there, because this is past these characters that we've already eliminated, and J can move ahead and refer to C, which skips over the A and B that we've eliminated at this point. So we've seen by means of the previous example that the Knuth-Morris-Pratt algorithm allows us to skip I and J ahead by fairly large amounts depending on the arrangement of our T and P strings. However, the question now arises, how do we know how far to skip ahead within T and P? So let's consider a few examples. Firstly, here we have our text T, which contains the string banana, and then we have a pattern P. So what we see here is that we have a mismatch between the first characters in both of those sequences, and we haven't found any kind of partial match yet. So what this means then is we can't skip I or J ahead any further. We just have to then skip ahead one space within our text T. So in other words, we're now comparing from the character A onwards, and J still remains then referring to the first character within our pattern P. Our next example is the one from the previous slide. So what we see here is we have already performed then a partial match that covers the blue characters highlighted in T and P at this point. However, what we see then is that the partial match within T ends with characters, specifically in this case the characters A and B, but it may be a longer sequence of characters. The point is that it ends with a sequence of characters that also appears at the start of our pattern P. So in this case, we can then skip ahead to match from after the characters A and B at the end of our partial match. So in other words, we are now skipping over the A and B at the start of P, as well as the matched characters within T, and we are now comparing C within our pattern P to D in our text T. So what we've essentially done then is we have moved P ahead 3 spaces to the right. Our next example is over here. So again, we've performed a partial match where we've matched over once again the blue characters in T and P. And now we have a mismatch between the pair of red highlighted characters over here. So what we see here then is we have a partial match within our text T, and this partial match does not end with characters that appear at the start of P. So you can see that the characters here at the end of T don't match to any of the characters right at the start of P. So in this case, we can then skip over the entire partial match, and we then begin again from the start of our pattern P. So in other words, we are now comparing from the first character within our pattern P to the next character within T after the partial match. In other words, the character D, as you can see over there. So effectively what we've done at this point is we have moved P then to the right by 4 spaces. Now what we see then is, by means of these examples, that the number of spaces that we can skip I and J ahead depends on whether our partial match ends with characters that appear at the start of our pattern, or whether that isn't the case, as in our second example over here. So as we've seen on the previous slide, we then need to determine whether the start of our pattern P matches to the end of our pattern P. Now, in order to do this, we first of all need to define 2 concepts. The first concept is the idea of a proper prefix. So a proper prefix is all of the characters within a string with one or more characters cut off the end of that string. So here we have an example. We have the string apple, and we can then cut off one character at the end of the string, in other words the E, which gives us the string APPL. We can cut off then one more character, in other words the character L, which gives us the string APP. And then if we cut off another character, we have the string AP. And finally, if we cut off the P, then we have just the character A. So all of these strings that we've constructed by cutting off the first character of the previous string are all considered to be proper prefixes of the string apple. The next concept is that of a proper suffix, and a proper suffix is essentially the mirror of a proper prefix. So a proper suffix is all of the characters in a string with one or more characters cut off the start of the string. So again, if we start off with the string apple, we can cut off one character at the start. That gives us then the string PPLE. If we cut off another character, we end up with the string PLE. Cut off another character, we end up with the string LE. And finally, if we remove the L, we end up with a string containing just the letter E. So all of these strings then that we have constructed are considered to be proper suffixes of the string apple. Now, the first operation that needs to be performed by the Knuth-Morris-Pratt algorithm is a pre-processing step that is applied to the pattern P. Now, this represents an efficient approach because, firstly, in general, the pattern P will be relatively short, meaning that there's relatively little pre-processing that needs to be performed. Also, this pre-processing step only occurs once, right at the start of the string matching procedure. Now, the pre-processing operation constructs a table, and this table has a column for each of the characters within our pattern P. So next we need to store a value for each of these columns, and we identify each column by a subscript j. So then what we do is for each column represented by j, we consider then only the characters in our pattern P that lie before subscript j. So in other words, we are dealing only with the substring that ranges from subscript 0 to subscript j minus 1 in our pattern. So then, considering only this substring, we determine all of the proper prefixes and proper suffixes within that substring. And we then compare proper prefixes and suffixes of the same length and determine which of these prefixes and suffixes match one another. When a match occurs, we record it, and once we've considered all of the proper prefixes and proper suffixes, then we store the length of the longest matching prefix within our table within column J. All right, so mathematically we can express this operation as follows. We are updating a value in the table for column J, and we store this value in an array called next at subscript J. So if J has a value of 0, in other words, we're dealing with the first column, then the value stored for that column is simply -1. In all other cases, we then need to consider a set of values k, which are defined in the range from 1 to j minus 1. And these values of k then are used to compute proper prefixes as well as proper suffixes of exactly the same length. So we compare then each proper prefix and proper suffix of the same length to check to see whether they match. And once we've gathered together all of these matches, then we record the largest of the lengths of these matches. Now, in all other cases, which essentially constitutes a situation where this range for k is invalid, we then just simply store a value of 0 at column j within our table. Right, so let's look at how this operation proceeds in terms of an example. So over here we have our pattern P, which consists of a number of characters. And we then have columns, one column for each character within P, and then our next array, which stores then our values for each column. So for the first column, when j is 0, we match this first condition over here, which means we store a value of -1. We then move on to the next column, so now we're dealing with a value of 1 for j. And we see then that the range of k values that we are dealing with are values of k that are greater than 0 and less than 1. Now, because k is a subscript, it needs to be a whole value, which means that this range then is invalid. This means that we are then dealing with the third condition over here, which means we then need to store a value of 0 within our next array for column 1. We then move on to a value of 2 for j. So now we are considering subscript 2, in other words, the third character within our pattern, and we consider then only the substring consisting of the characters prior to that third character. So we're dealing then with the string AA at this point. So now we need to extract all of the proper prefixes and proper suffixes. There's only one proper prefix, which is the first A within the substring, and there is only one proper suffix, which is the last A within this substring. So the proper prefix and proper suffix that we've extracted are both the same length. They consist of a single character, and we can see that those characters then match, which means that we then have a longest match of 1, which we then store at subscript 2 within our next array. So we can now move on to the next j value, a value of 3. So now we are considering the substring prior to subscript 3, in other words, the string AAB over there. Once again, we need to extract all of the proper prefixes and all of the proper suffixes. So all of the proper prefixes are then A and AA, whereas the proper suffixes are then B and AB. So we then compare proper prefixes and suffixes of the same length to one another. So we compare then the proper prefix A to the proper suffix B. That is not a match. Then we compare the proper prefix AA to the proper suffix AB, and that is also not a match. So we found no matches between prefixes and suffixes, which means then that the longest of those matches is 0, which is the value stored for column 3 within next. So we can now move on to a value of 4 for j. So again, we're considering then the substring that lies before 4, in other words, the substring AABA. So again, we need to extract all of the proper prefixes as well as all of the proper suffixes. The proper prefixes are then A, AA, and AAB, and the proper suffixes are A, BA, and ABA. So we now compare prefixes and suffixes of the same length. We see that the prefix of length 1 and the suffix of length 1 match. We see that the prefix of length 2 and the suffix of length 2 do not match, and we also don't have a match for a prefix and suffix of length 3. So what this then means is that the longest matching prefix and suffix are both of length 1. They only consist of a single character, which means that we store then a value of 1 for column 4 within next. Right, so we can then move on to a value of 5 for j. So again, here we're dealing then with the substring prior to subscript 5. So we're dealing with the string AABAA. So we then again extract all of the proper prefixes and suffixes. These are the proper prefixes for that substring, and these are the proper suffixes for this substring. So again, we can see then that the prefix of length 1 and the suffix of length 1 match one another. We can also see that for length 2, the prefix matches the suffix. For length 3, we don't have a match, and for length 4, we don't have a match. So this means then that the longest matching prefix and suffix are both of length 2. They're highlighted over there, which means that we store a value of 2 for subscript 5 within our next array. So we won't run through the complete computation of these values for the remaining values of j, but we can see then for subscript 6 we don't have any matching proper prefixes and suffixes, so the value there is 0. For subscript 7 we have only the prefix and suffix of length 1 matching, so we store a 1 value for subscript 7 in next. For subscript 8, we see that the longest matching prefix and suffix are of length 2. So both of those are then the substrings AA, which means we store value of 2 for subscript 8 in our next array. And then finally for subscript 9, we then see that we have a longest match of a length of 3 for the prefix and suffix AAB. So this means then that the longest match is then 3, which then gets stored at subscript 9 within the next array. So at this point we have now completely processed our pattern P, and we've constructed a full table which will now be used for the actual string matching. So now, assuming that we have successfully pre-processed our pattern P, we can move on to the actual string matching operation performed by the Knuth-Morris-Pratt algorithm. So the Knuth-Morris-Pratt algorithm is essentially, once again, an adaptation of the basic brute force string matching algorithm in much the same way that Hancock's algorithm was. So this is the pseudocode for the Knuth-Morris-Pratt algorithm. And we begin then with a call to this findNext function over here. Now findNext we will cover in detail on the next slide, but it is responsible for populating our table by means of our next array. Then we have these subscripts I and j, both of which start off with a value of 0, I being the subscript within our text T and j being the subscript that we are currently at within our pattern P. So in other words, we start at the beginning of T and P with our matching process. Now we enter this outer loop over here, and this condition then essentially just determines whether our pattern P can still fit into our remaining characters within the body of text T. So if there are fewer characters that remain within T than the number of characters in P, it means P can't possibly appear within T, and therefore we can stop our matching process with a failure. So then we have this nested while loop over here, and this nested while loop has two portions to its condition. First of all, it continues if j is equivalent to -1. So that is simply to deal with the first column within our pre-processed table. For all of the other columns, we then continue while j is less than the number of characters within our pattern P, and we continue then processing as long as characters within T match to characters within P at subscripts I and j respectively. So essentially what this condition means then is we continue matching through characters within our pattern P as long as the pairs of characters taken from our pattern P and our text T still continue matching. So at each step of that loop, we then increment I by 1 and j by 1. This just means we move on to the next character that we're comparing. And then once this loop terminates, we know one of two things has taken place. Either we found a complete match of our pattern within our text, or we found a partial match which has failed due to a mismatched character. So this if statement tests to see why the while loop has terminated, and if j is then equal to the number of characters within our pattern P, then we know that we've processed all of the characters within P, and so we have a complete match which we can report. We then just compute the subscript of the start of our match within our text T. Now, if we then reach this portion within our algorithm, this means then that we only have a partial match which has failed. So at this point, we then need to update j's value, and we do that by consulting our next array at subscript j, and then retrieving that value and setting j to that value. So notice then at this point that j's value is updated. It may potentially backtrack to an earlier position within our pattern T, but I never backtracks, so we only ever increment the value of I. And this is key to understanding why the Knuth-Morris-Pratt algorithm is as efficient as it is. So then finally, if we reach the end of this outer while loop, it means we have found no complete matches at all, which then just simply means we can then return with no match and terminate our algorithm's execution. So the main difference then between the Knuth-Morris-Pratt algorithm and the basic brute force algorithm is firstly that our partial match table, which is represented by the next array, is used to move j's value within P whenever a mismatch occurs. So that's handled by this line highlighted in red over here. And then secondly, I never backtracks to an earlier position within our text T. So in other words, I then only ever increments by 1. So let's look at the execution of the Knuth-Morris-Pratt algorithm in terms of this example. The first thing we need to do is populate our table as we did on the previous slide. So again, we have a value of -1 for the first column. Our second column at j's value of 1 gets a value of 0. Then at subscript 2, we don't have any matches between prefixes and suffixes, so we get a value of 0 there. At subscript 3, we also have no matching prefixes or suffixes, so we get a value of 0. Then at subscript 4, we can see that we have matches between the prefix and suffix of length 1, which each consist just of the character A. So this means that the longest match that we found has a length of 1. And then finally, for subscript 5, we see that the longest prefix and suffix that match there are of length 2, each of those being the characters A, B. So we then have a maximum length of 2, which we place in the last position within our next array. So now we've completely processed our table and we've totally populated our next array. So now we can continue with the actual string matching. So we then begin with I and j both having a value of 0, indicating that we're working with the first characters in T and P. So now we enter our outer loop and then we move into the nested inner loop, and we keep then incrementing I and j as long as they represent matches between the characters that are currently referenced in T and P. So A and A match, so we move on to the next character. B and B also match, so we move on to the next character, but now we see that we have found a mismatch between the character A and C. So at this point, we know then that we haven't found a complete match, which means we can't return a match, and therefore we need to update j's value. So we look in the next array at subscript j, and j's current value then is 2, so we're looking in the next array at subscript 2, which gives us then a value of 0, and this is assigned to j. So in other words, j then jumps back to the start of our pattern P. So now we again continue with our matching process. We see that we have a match between the characters A and A at subscripts I and J, so we advance. Again, we have a match for the character B. Then we again have a match for the character C. Again, there's a match for the character A, and once again for the character B. However, as we reach the last character within our pattern P, we see that we have a mismatch between C and D over here. So that means we failed to find a complete match, which means once again we need to update j's value. So j's current value is 5, meaning that we have to look in our next array at subscript 5, and we retrieve the value 2, which is then assigned to j. So now j jumps back to subscript 2, in other words, the third character within our pattern P. So notice that we've skipped over the first portion over here, which we've already matched within T. So now we continue our matching process again, character by character. We see that we are comparing two C's, so we can advance I and J. The A's also match here, so we can again advance I and J. The B's match, so again we advance I and J by 1, and then the final character within P also matches then the current character in T, which is D. So we increment once more, and now at this point our while loop terminates, and so we reach this if statement over here, and we see that J's current value is now equal to the number of characters within P. So this means we can then terminate with a match, and we then compute the start subscript of our match by taking I's current value and subtracting from that the number of characters in our pattern P. That then gives us the subscript of this first A over here, from which we can then deduce the entire matching portion within our text T. So at this point then our algorithm has successfully terminated and we found a match. So the question now is, how does this Knuth-Morris-Pratt algorithm function in terms of its overall execution complexity? So what we can see then is that as we ran through this execution, I essentially increases by 1 at each step, starting with the first character until it eventually reaches the end of a match. Now, obviously, the performance here then depends on the structure of T and our pattern P. However, in general, we can see then that the number of iterations that would be performed would be roughly equivalent to the number of characters within our text T. So in other words, the complexity then of this algorithm is equivalent to O of the number of characters within our text string T. The final detail that we need to discuss related to the Knuth-Morris-Pratt algorithm is how we actually go about placing values into the next array. Now, we've discussed this procedure in fairly high-level terms already, but we will now be considering what an algorithm actually needs to look like for populating values within our next array. So in a broad sense, this procedure involves matching prefixes and suffixes, but very importantly within the pattern P itself. Now, there are a variety of different ways that we could go about performing this matching procedure. And as I've previously pointed out, in a real-world setting, the pattern P is generally not very long. So this means we could just use a basic brute force approach to performing this matching procedure, and this wouldn't too negatively impact the overall performance of the Knuth-Morris-Pratt algorithm. However, it's also possible for us to adapt the Knuth-Morris-Pratt algorithm itself in order to perform matching between prefixes and suffixes. So once again, we have two subscripts, I and j. It's very important to note that these subscripts are both positions within the pattern P itself. Now, the subscript I is an index into the candidate suffix that we're currently considering, whereas the subscript j is an index into the candidate prefix that we are currently processing. So we then match candidate prefixes and suffixes, but after a mismatch then occurs, we need to continue processing with a new candidate suffix. So this then requires us to rewind our prefix subscript, in other words j, to a position that allows this matching procedure then to continue with a new suffix. Also, at each iteration of this algorithm, we need to store the length of the matches that we found within the next array. So over here we have the pseudocode for this algorithm. We're calling this algorithm findNext, and as we saw on the previous slide, the Knuth-Morris-Pratt algorithm calls findNext as its initial operation. So the first step that we need to perform is we have to place a value into our next array at subscript 0, and that value is -1. And this value will be -1 regardless of what our pattern P is. So we then just simply place that -1 value into our next array, in other words, the first column within our table. We then need to set initial values for our subscripts I and j. So I gets an initial value of 0 and j gets an initial value of -1. This -1 indicates that j is currently referring to the character just before the start of our pattern P. Obviously, the subscript -1 is an invalid subscript, so it's just a kind of a placeholder value for a position before the start of our pattern. So then we enter our outer while loop over here, and our outer while loop executes while I is still less than the number of characters within our pattern P -1. So essentially this loop will continue executing while there are still values that need to be placed into the next array. So while this is then still the case, we then enter our nested while loop over here. And this nested while loop will execute firstly if j has a value of -1. So this ensures that the loop will execute for j's initial value that we've set over here, but also if j's value is rewound to -1. The loop will also then execute while we still have values that need to be placed into the next array, and also if we have a match between a prefix and a suffix that we are currently processing. So in other words, if we have a match between our pattern P at subscript I and our pattern P at subscript j. So then in the body of the loop, we increment I and j both by 1, and then we need to place a value within our next array, and this value is placed at subscript I, and the value that we insert is the current value of j. So this value will then either be 0 if we haven't found a match between a candidate prefix and suffix, or it will be the length of a match if we have found a matching prefix and suffix. So then this loop will terminate once we have finished processing a candidate prefix and suffix, and so we then need to move on to a new candidate suffix, and we do that then by rewinding j's value. So we set j's value then to the next array at subscript j. Right, so let's look at how this algorithm then would operate in terms of a practical example. Over here we have our pattern P, and I've just separated the pattern P so that we can more clearly see how the subscripts I and J are updated and how they relate to prefixes and suffixes. Of course, in a real-world setting, we would just be using the string P directly, just with our subscripts I and J referring to different characters within that string. All right, so now we move on to the first operation within findNext, where we need to then set the value at subscript 0 within the next to -1. And as I've said, that -1 value is stored regardless of what P is. So then we need to set initial values for I and J. So we set I then to have a value of 0, meaning it's referring to the first character within P, and J's value is -1, meaning that it refers to a position just before the first character of our pattern P. All right, so then we enter our outer while loop because there are still there's still values that need to be placed into our next array, and then we enter the condition check for our nested loop over here. So we see then that our first condition succeeds because J's current value is -1, meaning we need to enter the body of this loop. So we increment then I and J, and then we need to update a value within the next at subscript I. I's current value is then 1, and we then store at that value in the next array J's current value, which as we can see is 0. So we then store a value of 0 within our next array, indicating that no match has taken place. So at this point, the nested while loop then terminates. So we move on to rewinding J's value, and we set that then to the next array at subscript J. So J's current value then is 0, meaning we reset J to the next array at subscript 0, which is then -1. So there we've updated J's value. We now need to continue with our next match. So again, we then enter the body of the outer loop because there are still values that need to be placed into our next array, and we then go to our nested loop. Once again, we can see our first condition succeeds, so J's value is -1, which means we enter the body of the loop and increment I and J. Now we need to update the value within the next array at subscript 2, which is I's current value, and we set that to J's value, which is 0. So once again, we then have a value of 0 stored within our next array, indicating that we haven't found a matching prefix and suffix yet. So then our outer loop terminates. We don't have any further matches between our prefix and suffix. So then we move on to resetting J's value. So J is then set to the value within the next array at subscript 0 again, which means that J's value is then updated to -1 once more. So now we move on to another iteration of the outer loop because, again, we still have values that need to be inserted into our next array. We then move on again to our nested loop, and once again the first condition is satisfied because J has a value of -1. So we once again then increment I and J, and then we update the value in our next array, this time at subscript 3, and we set that value to 0. So now we move on then to the next condition check for our nested while loop. We see J is of course not -1, but we can see that there are still values that need to be inserted into our next array, and we see then at this point that we have a match of the characters that are referred to by subscripts I and J. So this means we then need to enter a second iteration of our while loop. So again, then we increment I and j, and you can see then we've highlighted in red there the match that we found between a prefix and a suffix. So now we need to update once again our next array, and we update this then at subscript 4, and we then update that value to j's current value, which is then 1. So now we need to again then move on to the condition of our nested loop, and once again we see that we have a match between the characters at position I and position j within our pattern P. So again, we then enter our loop, we increment I and j by 1 each, and again you can see highlighted in red there we have the matching prefix and suffix. So then we need to again update our next array, this time at subscript 5, which is the last position in the array, and we set that to j's current value, which is 2. So at this point, we have now completely populated our next array. We then see that our nested loop then terminates. So the very last operation then that is performed is a resetting of j. So we set j's value to next at subscript 2, and j is then set to the first position within our pattern P. So at this point, our outer loop then terminates because we've run out of values within our next array, and so we have completely then populated our table. All right, so that's essentially then the operation of the findNext algorithm. The next thing that we need to consider is the complexity of findNext. So what we then saw through the execution of this algorithm is that i's value only increments at each iteration. So we basically move I from the first value within P all the way to the last value within P. So what this means then is that the number of operations that are performed would be approximately equivalent to the number of characters within our pattern P, and that then gives our asymptotic complexity for findNext. So finally, we then just need to consider the overall complexity of the Knuth-Morris-Pratt algorithm. And essentially then what we see is that we have the Knuth-Morris-Pratt algorithm that executes, but it then initially calls findNext, as I've previously pointed out. So essentially, we then have the complexity of findNext, which needs to execute, and then we add that to the complexity of the Knuth-Morris-Pratt algorithm itself for then actually performing matches between a pattern and a portion of our text. So in other words, the overall complexity then is equivalent to the number of characters in our text T plus the number of characters within our pattern P. All right, so that then concludes our lecture on string matching. All that remains to be said is for me to wish you good luck in the exam. So study hard, and I hope it goes well for everyone.